Welcome back, students. Now today we'll discuss on normal shock. Okay. Now in the previous lecture video, we already discussed on pressure distribution and choking in a nozzle for different cases like convergent nozzle as well as for convergent divergent nozzles. In the previous lecture video for convergent nozzle and divergent nozzle, when we discuss, it will show that particular when you change the pressure with the length of the duct, the pressure variations means back pressure variation with the length of the duct, it will show that there are some limit of the back pressure. So when you reach to this point, if you want to reach or if you want to decrease the back pressure below particular design back pressure line, that particular time that produce a shock wave or shock. Okay, so that is basically the causes of to produce shock in case of convergent nozzle as well as for convergent divergent nozzles. Now, as you know that shock are basically produced within the flow field due to the causes of irreversibility in the process, and there is abruptly change in certain flow field or certain flow parameters or certain flow properties. Okay, there are some changes. Now, this is basically the effect of the shock, and we know that basically shock are two types, that is normal shock and is oblique shock. Okay, now oblique shock basically the shock which actually normal shock basically defined when the shock wave front, when the shock is produced on a particular duct within the duct. Suppose these are duct are there, so when the flow field is there, if the shock wave is formed up there, the shock wave front is normal to the direction of the flow field, then the shock is called normal shock. Now oblique shock is basically a shock in which the flow when the fluid is flowed through a particular duct on a convergent divergent nozzle, or in case of convergent nozzle, so when they produce a particular shock wave front, and it is basically the direction that basically is produced, that is the oblique in the direction, so that's called the oblique shock. Okay, now we are going to the details in the normal shock. So what is normal shock? I think is a normal shock is basically highly localized irreversibility in the flow within the distance of a mean free path of a molecule. The flow passes from a supersonic to subsonic state, the velocity decreases abruptly, the pressure increases sharply. So there are some pointer there you can note down. Okay, so this is one point, this is also second point, and this is the third point, this is the fourth point. So that four main point that indicates if that shock is basically normal shock. Now suppose, as you know, that it is a particular duct are there, we are assuming that is a duct. Okay, when the flow is flow through a particular flow field or a particular channel or duct or convergent divergent channel, there are some shock are produced. Okay, and it is basically, if you define that normal shock or shock, that will be the it will be very interesting that shock is not shock in any fluid flow actually in certain circumstances when the supersonic flow, a very rapid change of pressure and velocity that takes place, and it is also that it is basically in the order of mean free path. Now basically we will be more interest to analyze the knowing flow parameters before the shock and after the shock without going to interior details. Shocks will only concentrate on the flow parameters. Okay, we'll only concentrate the flow parameters, and we assume that a discontinuity in the flow field in the upstream as well as downstream. And suppose this is the upstream of the fluid flow when the fluid is flowed through a particular channel, and this is the downstream. We assume there is an upstream and this is the downstream. This is the upstream and this is the downstream. In the upstream of the flow field, the designated some flow parameters. Suppose these flow parameters like velocity as designated with Vx. Similarly, for this, for in the if the fluid is flowed through a particular direction in this direction, if the upstream flow field, the parameters is designated Vx, velocity, as like Px, that means pressure, that is rho x, that means density, and as well as Hx, that means the enthalpy, right? Now, in the right side of the flow field, that means the downstream section of the flow field, that designated with the properties like Vy, Hy, and Py, and as well as rho y. So these are the properties in the upstream as well as downstream. Now, This is the thin shock wave. As we know that actually shock are basically small things. It's basically the distance is a mean free path of a distance, mean free path of a molecule. It's very short producing time, and this very short length, the short duration of time that can produce. So this is, we are only concentrated the thin shock wave within the flow field. Now we are concentrated on this region. This is surrounded by, suppose this is a control surface. So this is a control surface as designated. And now we are more interesting to analyze that the flow parameters, the flow properties, okay, the flow properties which are basically in the upstream direction as well as the downstream direction due to the shock, means due to the normal shock. Is there any changes, or is there any not, there is no change at all due to shock, okay. So there are some variation. We are only concentrate on this in details. Now going to the next, that there are lots of other point, okay. Now basically as you know that if you suppose this is a thin shock wave and this is the control surface area. Now if you write down the energy equations, energy equation means, as you know that enthalpy equation, that means total and total energy, that means H plus V square by 2. If you apply that for upstream as well as for downstream, that means Hs plus Vx square by 2 is equal to Hr plus Vy square by 2. Right. Now X denotes the upstream, Y denotes the downstream direction. That will be equal to the H0x is equal to H0y. What is 0x, 0y? That indicates the stagnation enthalpy of X direction, means stagnation enthalpy of upstream direction and stagnation enthalpy in downstream directions. And obviously when the fluid is flow through a particular duct, it will be that flow should be in adiabatic and flow should be the reversible in nature. So that's why when you consider there's a thin shock wave, there is no heat transfer takes place, then we can get the steady flow energy equation that in terms of that. So Hx plus Vx square by 2 is equal to Hy plus Vy square by 2 is equal to H0x, that will be H0y. So now if we apply the continuity equation, as you know that the mass flow rate from the upstream direction is equal to mass flow rate to the downward direction. So mass flow rate in the upward directions, mean upstream, that equal to rho x into Vx is equal to rho y into Vy. Why is not A here? Because A is the cross-sectional area through the shock wave. So A is both the same in both the cases, and it's very thin shock wave. That's why A is cancelled in both the cases. That's why the equation becomes rho x into Vx is equal to rho y into Vy. That is for continuity equation in the control surface. Now, if we apply the momentum equations along this, you can write down the momentum equations. And now if you apply that, in case when you write down the momentum equations, now suppose when the fluid is flow through a particular channel, we assume that there is no friction flow. Actually there is no friction at all. That then you can write down the momentum equation in this form, that actually net pressure force, that will be Px minus Py into A, that means P into A means that is basically force. Now Px minus Py into A, that means the net pressure, net force is equal to mass into velocity, that means mass m dot is equal to Vy minus Vx, okay. Now m dot means mass flow rate, that equal to, you can write down rho y Vy square is equal to minus of rho x Vx square. So in terms of that, you can write down Px plus rho x Vx square is equal to Py plus rho y Vy square. So basically a P plus rho into V, that is nothing but impulse functions. Okay, these are impulse functions. These are basically flow properties, and that is basically nothing but is the summation, is a product, or is equal to the pressure plus product of density into velocity of the fluid. This is the impulse function which indicates the flow parameters. So this is the impulse function in the upstream direction, and this is the impulse function of the downwards direction. So that will be equal. So Fx is equal to Fy. Okay. Now, as you know, as we go beyond this equation of state, as you know that equation of state are basically H, you can write down H is equal to H is a function of S and rho, and S is a function of S is equal to P and rho. As you know that is the equation of state, you can say that it's also implicit function relationship. Now, you know that in thermodynamics, if you want to express a particular thermodynamic property, dependent property, you can in terms of you can apply or you can express two independent properties. Okay, so in terms of that, you can also express enthalpy as a function of entropy and density. Similarly, entropy is something is independent of function of pressure as well as density. Now, if you know that now, if you want to know the locus of a point in a HS plane, if you want to draw a locus of a HS plane, suppose this is a HS plane. Now, if you want to draw a HS locus of a HS plane, now suppose you know that you just fixed, okay, you know, you just fixed, there are some properties like Vx, Hx, rho x, Px, Hx. There are some one more questions to you. You can tell me that there are some properties are there. Suppose you assume that there are some I have question to you that if I got certain fixed state in upstream, if I have certain fixed state in upstream, whether it is possible by shock to attain several state of downstream or not, the answer will be no. Mathematically, there is a unique state corresponding to a given state of upstream. So to do this, let us find out locus of all point in HS plane and which correspond to same stagnation enthalpy, and satisfying quantity equation, energy equation as well as equation of state. So first we have to fix that that properties like enthalpy, velocity, pressure, density. First we have to fix this point. Okay, now if you fix this point, now if you apply hx plus vx square by 2, you can get the value of stagnation enthalpy in x direction. Similarly, if you know that, now if you choose the value of vy, suppose here, so from the stagnation enthalpy, because hox is equal to hy, so that equal to, if you choose vy in the particular downwards direction, you can get value from this here. So you can get values from hy. Now if you know the value of vy, so as you know, the for a particular mass flow rate, so rho I vy is equal to constant, so mass flow rate or q. Now if you know the value of q and if you know the value of vy, so corresponding to this you can get the value of rho I also. So from this you can easily calculate the or easily concluded or easily formed particular dependent, as you know that h is a function of s and rho. So from this you can easily calculate the value of s. So from this concept you can apply. So, so this is the HS line in which you can see this is the Fanno line, and in the Fanno line, in a Fanno fluid flow line, you already know that Fanno fluid flow, actually that type of flow in which the flow basically, or fluid flow basically frictional and adiabatic flow. Okay, and obviously this is a irreversible type of flow. There is no reversible process at all. And this is a diagram, and from locus of that you can draw a diagram corresponding to this. It will looks like this ones. Okay, so this is the O point, this is the O point, this is the middle point of this curve. So this is the O point. Now as you know that this is the in the Fanno line, in the Fanno fluid line. Now as you know that here, this is the point O. It suggests that in this point actually, so this is the ds by dh is equal to positive. In that point ds by dh is equal to 0, and in this portion of the curve, this is basically ds by dh is equal to negative. Now, so as you know that the Mach number, the value of Mach number, if the Mach number values is basically greater than 1, then basically it is basically called supersonic flow. And if Mach number value is less than 1, then it's called subsonic flow. And Mach number is equal to 1, that is called sonic flow. Now, in this diagram, in this HS diagram, what you can see that by the locus of by the application of different energy equations like energy equation, quantity equations, and momentum equations, we can able to draw a diagram, and it looks like say line like that, in which it can basically represent the line which indicates the Mach number is greater than 1. That means that flow is basically supersonic flow. Okay, if the Mach number is greater than 1, that means from this region to this region, they basically is called supersonic flow. It indicates. Now is point O here, that indicates, that means ds by dh is 0, that means m is equal to 0, that means Mach number is 1. Okay, Mach number is 1. Okay, sorry, it is 1 maybe. It is Mach number is 1 in this point O, where ds by dh is equal to 0, and that means is the sonic, this is a supersonic flow, this is a sonic flow, and in this region Mach number is less than 1. That indicates that is a subsonic flow, where ds by dh is equal to negative. Now, as you know that ds by dh, suppose this is the point. Okay, as you know, this is the point, first point we are occur actually for the upstream in the fluid flow. And if you want to now, can you tell me that what is the point if you want to another point? Suppose this is the point, if you want to increase the, suppose this is a change of, suppose this is a duct in which the fluid is flow through a particular region or particular fluid flow, particular fluid parameters, with fluid parameters. Now if the fluid is flow through a particular channel or duct, it can maybe happen that there are some frictional will be, there are frictional generated, because Fanno line or Fanno fluid line is basically this type of fluid flow where the frictional we are considered here. So that means the frictional force, the friction will be occur within the fluid flow line. That means when the friction will takes flex means action takes into the place, so that means the velocity, that means the velocity of the fluid flow will be decreased. So when the fluid flow, when the along the duct line, when the fluid is flow through the along the duct, the velocity will be slowly decrease. Okay, and it reach up to from the supersonic to sonic velocity. So in this line, when this point is basically here, when it will be reached to this point, that means the frictional along the, it indicates the fluid flow along the duct line. When it is flow through the along the duct line, that means the friction is basically decreased, means friction will be increased. Okay, frictional if they increase throughout the duct when the fluid is flow, that means velocity is decreased. At that condition, if the velocity is decreased, that means the fluid velocity is decreased. That means what? That means the fluid is basically transformed from supersonic to sonic velocity. So that's why it's just to that's why it is reach up to the this point. Now, if the fluid is something at this point, it indicates this point. Now, if the fluid is increased, if the fluid is flow through a particular duct, what happens? The velocity, the friction will be takes into the actions. Okay, if the friction is will be taken into the action, that means the velocity will be decreased. Okay, that means that velocity also change from subsonic to sonic. Okay, now as it is suppose this is the point, as the point is increased in this direction, that means as we know that this is a fluid flow, Fanno fluid flow, basically adiabatic flow, adiabatic universal type of flow. That means adiabatic means dq is equal to 0, so ds will be increased. As you know that from the entropy principle, the entropy basically is obviously for isolated system is basically increasing all the time. That means increase all the time. That means the HS diagram, it indicates this point is here, this point is here, this point is here, this point is corresponding here. That means entropy is increasing throughout the duct when the fluid is flow through a particular duct. Now, this is the basically significance of Fanno of fluid flow of Fanno line. And now, suppose these are as you know that uh, this is the equation that indicates basically steady flow energy equation, that is basically continuity equation that indicates this is the momentum equation. Now it also sometimes also written as like dh in terms of h plus b square by 2, also written as dh plus d into basically it is a differential form. So dh plus d into b square by 2 is equal to 0. It also written as dh plus vdv is equal to 0. Now, so it will be written as VdV is equal to that it is VdV. VdV is equal to minus dH. Okay, this is the energy equation. You can also written in this form also. Now, you know that this is the rho x. Already we discussed that rho x into Vx in the upstream direction is equal to rho y into Vy in the downwards directions. So it also written as rho into V is equal to constant in shortly. So if you differentiate in logarithm, if you do logarithm differentiation, that will be produced that d rho by rho is equal to dv by v is equal to 0. That means dv is equal to minus of v into d rho by rho. Okay. Now, if you apply the thermodynamic relationship, TdS equal to dH minus VdV. You already know that from the basic engineering thermodynamics. You have some idea from the first law of thermodynamics. You know that dq is equal to du plus dw, and in terms of that, dq is equal to TdS. Okay, so from that concept you can apply. You can get this equation TdS equal to dH minus VdV. Right. Now TdS equal to dH minus VdV. In terms of dP, V here, V as you know, V is equal to 1 by rho. So in terms of that, you can write this equation TdS is equal to dH minus dP by rho. Right. Now here in both sides, if you divide with dH term, that the expression will be TdS by dH is equal to 1 minus of dP by rho divided by dH. So this is the another form of thermodynamic property relationship in the context of compressible fluid flow. Okay, in the normal shock, when you discuss in normal shock. So, and you know that what happens in the HS diagram in the Fanno line. So this is the Fanno line that indicates the Fanno line. At point O, what happens? That point dH by dS is equal to 0. At same time, m is equal to 1. That means Mach number is 1. That means that sonic velocity or sonic fluid flow is occurs within the duct at that time. Now, as you know that at point O, ds by dH is equal to 0. As you know that at point here, ds by dH is equal to 0. Because this is the age is a s, so dh means ds by dh will be obviously 0 because this is the maximum point. Okay, now as it is dh by dh is equal to 0, now you know that from the thermodynamic property relationship, T into ds by dh is equal to 1 minus dp by rho divided by dh. If you put this condition ds by dh is equal to 0 here, then you can get dh is equal to, so this one is equal to 0. If this one is equal to 0, this one is equal to 0, so dH will be is equal to d rho by rho. So this one, okay, means dP by rho. Okay, so dP by rho, dH is equal to dP by rho. Now, from energy equation. So as you know that from the energy equation, so this is the energy equation. In terms of that, you know that energy equation gives you that VdV is equal to minus dH. So VdV from the energy equation, VdV is equal to minus dH from here. Okay, VdV minus dH. So VdV is equal to minus dH. VdV is equal to minus dH. Minus dH means dH already you know the from the thermodynamic property relationship. dH is equal to dP by rho. So in terms of that, dH also written as dP by rho here. Okay, in terms of dH now, and you know that dV here V into dV. So dV in terms of that from the continuity equation, dV is equal to, you already calculate minus of d rho by rho. You can put here, okay, in terms of dV here. In terms of dV, you can put here from this equation. So dV is equal to minus V into d rho by rho is equal to minus dP by rho. Okay, so minus minus both sides is cancelled. So that equation will be becomes V square is equal to dP by d rho. So V will be under root of dP by d rho. Now, so at this O point means at the sonic velocity fluid flow point or at the maximum flow rate condition point, the V means velocity of the fluid, that is equal to minus under root of dP by d rho. So it is a condition for sonic velocity as we consider firstly that the fluid is flow through a particular channel or duct or convergent divergent channel or any type of duct. The condition was that fluid is flow through a particular adiabatic conditions. So adiabatic condition means there is no heat transfer takes place. So at that particular time when you calculate the velocity of that particular point, that gives you the velocity of that particular sonic velocity, that will be V is equal to minus delta P by delta rho at constant S. So that gives you the sonic velocity. Okay. Now, So that gives you the sonic velocity. Now, what happens? So this it is ds by dh is equal to, so h is equal to 0. When you apply that, you just get the sonic velocity that is equal to, means, and fluid velocity that equal to actually sonic velocity, means fluid velocity means sonic velocity, that means velocity of fluid is equal to acoustic velocity or velocity of sound particular at point O. Now, in this region of the curve, what indicates that n greater than 1, n greater than 1 means ds by dh is positive, means ds by dh is greater than 0. That means it indicates that Mach number value is greater than 1. That indicates it's basically supersonic type of fluid flow. That indicates that dp by, so from this expression, if you put this condition here, you can get that ds by dh is greater than 0 or positive term. If it is a positive, that means dp by d rho divided by dh less than 1, right? So dp by d rho is less than dh. Okay, from the energy relationship, you know that vdv minus dh, okay, vdv minus dh, and dv is equal to d rho by rho. Okay, vdv and dv, sorry, vdv is equal to dv and minus dh. So v square d rho by rho, vdv is equal to, as you know that vdv is equal to, okay, vdv is equal to v square d rho by rho is equal to dh, and v square is equal to dh into rho by d rho. So v square is equal to, as you know, the v square, it should be, v square should be greater than dp by d rho, because as you know the v is equal to, when the Mach number is 1 or ds by dh is equal to 0, that at that condition, or at that condition, v should be the d under root of dp by d rho at constant s. Now when ds by dh is greater than 0 or positive, it would be v square should be greater than dp by d rho. So v should be greater than this term. This term means that indicates your sonic velocity or acoustic velocity. So v greater than, so velocity of sound, that indicates. So in this region, this indicates the velocity of sound. It velocity of fluid actually greater than the velocity of sound. When the fluid flow reach this point, it indicates that it reached the sonic velocity. Okay, so similarly, so when you transform this line, it also gives the sonic velocity term. If you put this condition that ds by dh is negative, then you can get that v less than a. Okay, so this is the condition for Fanno line, and one fluid flow line also are there, so we can discuss now. As we know that, so these are the Fanno line that gives you the idea when the fluid is basically adiabatic and friction are there. Okay, so there are friction are present. Okay, now actually there is no actually friction at all. So phenol-line are that type of flow when the fluid is flowed through a particular irreversible in nature. Now with Rayleigh line, R-A-Y-L-A-I-G-H, Rayleigh line, it indicates, Rayleigh line basically indicates that basically it's a reversible. Okay, that's a basically reversible, and obviously heat is taken, means diabatic flow, and phenol-line was the adiabatic type of flow. It's a diabatic flow, means heat transfer takes place. Okay, heat transfer takes place. Okay, and if you draw the diagram of Rayleigh line in HS plot, in similar fashion, you can get that it looks like, say, these two types. In this point, the phenol-line was, so the phenol-line was this one. So this is the maximum point. Similarly, this point is also your maximum point, and this indicates the Rayleigh line. Okay, it's a basically reversible, and when you consider that friction is absent at all, the friction is absent, and if you put this condition on the different types of continuity equation as well as energy equation as well as momentum equation, then you can get this type of curve, and that basically indicates a one type of reversible type of flow. Okay, and basically it's a diabatic type of flow, and it indicates the Rayleigh line, and basically we take basically we consider the continuity equation, and as well as momentum equation and equation of state. Continuity equation, momentum equation, and equation of state, both equations are considered when you draw the HS plot, and that line basically gives you the Rayleigh line. And in this line or in this fluid flow, it gives you the idea about when the fluid is flowed through a particular duct or a channel in which the friction are absent here, and the process is basically diabatic type of flow. That means heat transfer takes place between the system and surrounding, and it's basically reversible in nature. And in case of phenol line or phenofluid flow, it indicates that basically the fluid flow is basically irreversible in nature and adiabatic type of flow, and we are considered that the friction are present. So this is the difference between Rayleigh line and Fanno line. And Fanno line indicates the basically adiabatic irreversible type of flow, fluid flow, and in case of Rayleigh line indicates the diabatic frictional type of flow. Okay, so this is the normal shock, and we in the next class actually we already we discuss on the normal shock in an ideal gas. Okay, okay, thank you very much for listening and watching me.